Assalamu alaikum, Bismillahirrahmanirrahim. I hope you all are good and well in your homes and stay away from corona. So today we will start and solve numericals related to polytropic process that we already discussed in the last lecture of 5 and 6, and also done a very simple numerical of isothermal process. So today we will start polytropic process numerical. So before starting this, once again let's revise the last lecture topic, so we can easily and smoothly solve numerical related to polytropic process. So first of all, I would like to revise that we have two process in the start: compression and expansion. After this lecture, we will also perform the whole process cycle, in which we have all the process like compression, expansion, adiabatic expansion, so on in Carnot cycle. But in the start, we are restricted only to compression and expansion. So first of all, we have to understand compression and expansion process. For easiness, I also put GIF image, which by animation you can easily understand the expansion and compression process. For an example, this air comes in the cylinder, then this valve is restricted, then when the pistons closer to the cylinder, the gas compress, and then the discharge valve open. So when the gas is releasing from this point, it is compressed, and if we reverse the process, then it is expansion process. Simple, it can understand with this picture too. When this piston comes in closer to this bottom tank cylinder, the gas is compressed, and during compression the chart will move on like this. Sorry, expansion process. If it is an expansion process, then the process is like this. This is state 1, this is state 2. So the pressure rise, pressure decrease, volume rise. But in opposite to that, when we have opposite process, sorry, when we have opposite process, the piston goes toward the cylinder, then it is a compression process. This is point 1, this is point 1, and this is point 2. So the processes goes like this: the volume will decrease, the pressure will rise. This is the process cycle path that already had discussed in the previous lecture. And this points, how we identify this point, it is defined by the n. We already studied that polytropic process equation, that PV n is equal to C. So we have a numerous path with respect to n, that if the n is equal to 0, if we put PV 0 is equal to C, then what happen? Anything which has any variable which has power of 0, then it is 1. So P is equal to C. So it becomes, pressure is become constant. So it is becomes isobaric process. But if in the case when PVN is equal to 1, so it is PV is equal to C is a process equation for isothermal reaction, isothermal process. So it becomes this. So and showing how the path will differ from this point. When the n power is greater than 1, 1.2, 1.3, and when it goes to 1.4, then it's called to be adiabatic process. And in the similar way, when the power of n increase and goes into infinity, then PV power infinity is equal to C. Then in that case, the volume is become constant. It is a we have a derivation in between this solving this equation, but in that case volume becomes constant and it becomes isochoric process. So these are the four processes that already discussed in the last lecture, but today we will prove it from this equation. Polytropic process is a general process by in which by replacing the value of n we have a multiple process like isobaric process, isothermal process, adiabatic process or isochoric process. So today we are going to solve this numerical. We already discussed that to how we can calculate the work in this compression process or expansion process by simple equation of integration P dV. So we already discussed that what about path function, how the path function makes effect on the overall work done during the process. We already discussed in the last class. We cannot use the simple equation of work is equal to P del V. In first year or pre-engineering, you studied that equation. That can be also applied, but we have limitation in this equation. We didn't get very accurate answer from this equation as shown in this diagram. So initially, by understanding the system, it is easy to use that equation, but now you are doing engineering, so we have to use advanced equation like integral PV dV. And we already discussed that there is some experiment and machines which calculate the polytropic variable n, by which we decide it is a adiabatic process or is a isothermal process or in between, what is the value of the process or how, so we can accurately calculate the work done during the compression or expansion process. So these are the I have to solve this equation in here, but I already solved in previous slide. So let's move on. These are the basic four process in thermodynamics. This equation we already this numerical we already solved in the last lecture. Today we are going to solve this example 2.1 from the book of Morang. It's a solve example. You can also see the solve example in books folder that I already shared in the Google Classroom. But today we will solve this numerical here. So first of all, we have to read this numerical. A gas in a piston cylinder assembly goes an expansion process. Look, it is an expansion process for which the relation between the pressure and volume is given by PV power n is equal to constant. That is same equation, PV n is equal to C, and in this case n is 1.5. And these are the initial data. The initial pressure is 3 bar. The initial volume is 0.1 meter cube and the final volume is 0.2 meter cube. So initially it has volume of 0.1, then it moves like this, then it goes to 0.2 meter cube. Determine the work for the process in kilojoules. So we have to find its in kilojoules, so we need to put the pressure in kilopascal, so we already get answer in the kilojoules. If n is equal to 1.5, that already shared in previous point. So now we are going to solve this numerical in S note. Here we go. So first of all, we write the equation work done is equal to P dV. Let's see, V is equal to integral from process 1 to 2 P dV. Okay, so here here in this case the equation PV and is equal to C. Now we replace P is equal to C upon V power n or CV minus n. V goes variable to numerator, the power goes in the minus form. So we can directly write this like minus n dV. Now C is a constant, it goes. So in the last numerical, the equation is simpler. It is a 1 over V. It is isothermal process, so it is 1 over V, and integral formula of 1 over V is simple, log V, and by applying the limits, this is log V2 minus log V1, and then applying the log formula, we have ln V2 upon V1, and we put the parameter initial state conditions. Then so we in this case we have a V minus n dV, so we apply a simple numerical of simple solution of integration, that is V minus n plus 1 and minus n plus 1, applying limits from 1 to 2. So this is simple integration of V power minus n dV. So we move on towards next page. So now we get a simple equation of work done, that is C multiplied by V minus n plus 1 and we have a limits 1 to 2 minus n plus 1. Now we have to multiply by this V with the V, but we know that PV n is equal to C. So for process 1, C is equal to P1 V1 n power V power n, and for process 2 it is like P2 V2 power n. So when we open the limit, we applied the appropriate formula with respect to limits. Now when we open this, applying the limits, V2 minus n plus 1 minus V1 minus n plus 1 and divide by minus n plus 1, we can write 1 minus n. It is the easiest way. Now when we multiply by C with V2, we open the formula P2 V2 power n. To make it simpler, we can apply all the limits over here. We know that V2 is 0.2, V1 is 0.1, n is 1.5, and when we can apply 1.5 and V2 and V1 value and solve this numerical easily. But I'm sticking here because I want to solve this numerical for a general polytropic process. Once we form a equation of work done in the simpler version, we can solve it later by simpler equation. So basically we are driving the equation of work done for a general polytropic process. So I'm sticking this variables and this powers in its initial form till we can simpler equation. So that's why we are multiplying C P2 V2 n with the V2. So we can write P2 V2 power n and V2 minus n plus 1. So n can be cancelled out. Similarly, when we multiply C with V1, we open the formula P1 V1 power n multiply by V1 power minus n plus 1. So we can cancel out this power and we get very simpler equation or derive the equation for the work done for the polytropic process. So now the equation becomes P2 V2 minus P1 V1 divided by 1 minus n. So now it's become very simple equation and we derive with this equation for all polytropic expansion or compression process. So this is the equation. Now we are applying we can easily apply the equation the limits of P2 V2 n and solve the numericals, and we can use this formula in later numericals. We don't need to apply the whole formula of work done integration PDV and open the limits. We get simpler equation and then later we can apply this equation easily. So now we are applying the limits. It's P2 V2 minus P1 V1 1 minus n. Sorry. Now we have to calculate P2. So we are applying we are equating this C is equal to C, then C is equal to C, then P1 V1 n is equal to P2 V2 n. So we can write this P2 V2 n is equal to P1 V1 n. Sorry, it's P2 V2. Now P2 can easily be calculated by putting this V2 over there. P1 we know that it's a 3 bar, and 1 bar is equal to 1 bar is equal to 110 की power 5 Pascal. So in that of kilopascal it is 100 kilopascal, and for 3 bar it is 300 kilopascal. So we can write directly 300 because we want to get the answer in kilojoules. So we have to put Pascal in pressure in kilopascal. So we can write 3 bar in 300 kilopascal. 3 bar is equal to 300 kilopascal. So this is P1 multiplied by V2. V2 is we know that V2 is 0.2 and power 1.5. It's 1.5 divided by V2 is 0.1 power 1.5. So we get the answer P2 is 106 kilo. Sorry. So we get the answer of P2, and then we have to place P2 over here. It is simple 106. V2 is multiplied by 0.2 minus P1 is 0.1 and V1 is 0.1 and P1 is 300 divided by n is 1.5. Then we get answer is positive, because by solving this equation we get positive answer. It is 17.6 kilojoules, because why it is coming in kilojoules, because we set the pressure in kilopascal. If we place it like this bar into Pascal, then the answer comes in joules. Then we need to divide the whole answer with 1000 to get kilojoules. Now we get directly answer in kilojoules. And why it is positive? We already discussed sign convention in the lecture 5 and 6. What are the sign convention? when the heat is added to the system, we take it as a positive because it is increasing the internal energy. When heat is releasing from the system or releasing from the system, so it takes negative. And the for work done, it is opposite because in the equation we have a sign of minus sign. So when work is added to the system, it is for the heat transfer, it is positive, and for the work done it should be negative. And when the work done from the system, then it should be positive. So in this case, it's showing that the expansion process takes from the system, not by the system, not by external force, but it is giving external force to some other process. Now we solve this numerical. Let's move towards, yes, determine the work for the process in conclusion. The work is 17.6 kilojoules. We solve this example 2.1. Now the similar numerical with the different requirement. It is a it is a continuation of this numerical. It is example 2.2 from the Moron, or it is a similar numerical in Sangel 4.3. I change the values with the with 2.1, so it becomes the extension of this numerical. In this equation, in this numerical, let's read out the first and then we will solve. It is extension of previous numerical. 4/10 kilogram of a certain gas is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure volume relation is this: PV 1.5 is equal to constant. The initial pressure is 3 bar, the initial volume is 0.1 meter cube, and the final volume is 0.2 meter cube. The change in specific internal energy of a gas is in this process is U2 minus U1 is minus 55 kilojoules per kg. So it is also showing that it is work from the system, because minus 55 kilojoules of internal energy is decreasing. The internal energy is decreasing. So where it goes, it goes into the work. This energy goes into the work. There is no significant changes in the kinetic and potential energy determine the heat transfer in this process. So now in this numerical, it is asking heat transfer, and by for the closed system we apply the same formula that we will apply the same formula that sum of all energies is equal to Q minus heat transfer minus work done. So it is a more simpler numerical if we have a continuation of the previous numerical, and if we know the simpler derived equation of work done, that is P2 V2 minus P1 V1 upon 1 minus n. If we change, even if we change the value of n, if we change the value of n from 1.5 to 1.2 or 1.3, we need to apply the same formula P2 V2 minus P1 upon 1 minus n and replacing n with 1.3 or 1.2 and get the work done. And then we apply the same formula for the sum of all energies is kinetic potential internal is equal to Q minus V. So now solve this, we can solve this numerical as well. Let's note we save this. Make new equation. So for this numerical we can solve, we can directly use the work done 17.6 kilojoules positive, because it is a continuation of that numerical. But if we have a different value of n, we need to solve it again with P2 V2 minus P1 V1 1 minus n. So sum of all energies delta E is equal to Q minus W, and delta E is sum of change in kinetic energy, change in potential energy plus change in internal energy is equal to Q minus W. We know that there is no change in potential, so we can set it as 0. We know that there is no change in kinetic energy, so we can also write as 0, and delta U is simple U2 minus U1. But let's see, have they given us capital U or small u? In the numerical, you can say that they have given us a small u2 minus u1, and the unit is not kilojoules, it is kilojoules per kg. So it means that it is a specific internal energy. It's a specific internal energy. What is a specific internal energy? Is simply divide any parameter or any properties with the mass, so it becomes a specific, like a specific volume, a specific internal energy, like the unit of volume is V, but the specific volume is small v. And by equation in the similar way, the internal energy is U, the unit is kilojoules, but specific internal energy is small u, like showing over here. So it's a simple formula. The capital U is basically mass multiply first we need to formula for specific so specific internal energy simply is capital U, the internal energy divided by mass. Anything which is divided by mass becomes specific internal, a specific property, like a specific volume, a specific internal energy. This is not is equal to this. So in numerical, we have to we need to put the value of U. So what the value of U is? Simply U is equal to M multiplied by small u. It is capital U, it is small u. So we can write mass, and they also telling us the mass with the, that is 410 kilogram. 4 tens means 4 upon 10, 410 kg. Now we can write this here. Simple, this is M u2, small u2 basically, minus M small u1 is equal to Q minus W. Mass is constant, so we can take this like this, u2 minus u1 is equal to Q. We need to calculate the Q, and we already know that the work is 17.6. This minus is from the formula. If we have a work in the negative, then it becomes positive. And we know the answer of u2 minus u1, it is minus 55 kilojoules per kg. You can see here minus 55 kilojoules per kg, and the mass is 4/10. So we can write this mass 4/10. We have to write in the negative form because Q is equal to 17.6. Let's solve this in 410. Sorry, minus 55. It is in the negative form, then the work becomes positive, is equal to Q. So 17 goes here, becomes positive, and 410 multiplied by this. So by solving this, yes, now so it's become minus 22. 4 upon 10 multiplied by 55 is minus 22 plus 17.6. Sorry, 17.6. So we get the heat transfer in negative minus 22 plus 17.6. The answer is 4.4 kilojoules. So it's a negative 4.4 kilojoules. Remember that it is a continuation of previous numerical, so we take work done directly from the previous numerical, but in the case we have a different value of n like 1.3, 1.4, then we have to calculate either by simpler derived equation P2 V2 minus P1 V1 1 upon 1 minus n, or work done is equal to integral PdV. So here we get the answer of Q, but we have a negative answer. It means that heat transfer is losing from the system. In this process, heat is a heat loss from the system, and if it is a positive, then heat is added to the system, and you can easily identify by this also. Internal energy is also decreasing from process U2 minus U1, it is minus 55. So by this you can also make a guess that in this process heat is releasing from the system, not added. So I hope you understand this numerical. It is not a very difficult numerical, it's simple expansion process. Both numerical are easy. Let's move on to the next topic. We have done numerical, and by ending this lecture 7, 8 and 8, I will also share practice question in Google Classroom tab. Not in the not here in the lecture, but later on in the classroom I will share practice question, so you can also make practice by yourself to get aware of that these numericals and easily solve in the paper 2. So let's move towards the next topic, that is phase of the pure substance. A pure substance in thermodynamics, especially a pure substance is that is uniform and invariable in chemical composition. A pure substance can exist in more than one phase, but its chemical composition must be the same in each phase. Like for an example of water is a pure substance in which the composition, whether it is in the solid phase, whether it is in the liquid, or whether in the vapor, it will not react further if we itself. So it's we can say it's a pure substance. And even for the composition, like in shown here over there, it is nitrogen. Like here in the nitrogen, the composition is only nitrogen, and it doesn't have any further any other other formula or other element in it. So you can say that it is a pure substance. But in thermodynamics, anything which is not changing its chemical composition throughout their three phases, like solid, liquid, gas, it can be called as a pure substance in thermodynamics. Like even for the water will not change its composition whether it is in the solid. Like water is not changing its phase in whether it is in the liquid, solid, or gas. In solid it simplifies, in liquid it is water, and in the gas it is a steam. So it called a pure substance in thermodynamics. This is a basic definition of a pure substance in thermodynamics. Let's move on. So why the first question arises that why we are talking about pure substance, or why we are studying this pure substance in thermodynamics? Because in upcoming numerical we have to solve the numerical with the process of phase change of a pure substance, in which the chemical composition is not changing, but the state is changing, and we have to discuss, or we have to analyze by which form of the phase of the substance produce work and how it is transforming or converting power from one end to another. For an example, like a practical example, you already listen the name of thermal power generation in most of the news, and that Pakistan 60% of power capacity is based on thermal power generation. So what is thermal power generation? Simply in most of the mega power generation, we are converting heat into the power. How? Like nuclear energy. Nuclear energy cannot create power itself, it is producing heat. We first produce steam from that heat. We are utilizing that heat to convert that water into the steam, and when we form a high pressure temperature steam, we pass it into the steam turbine, and then by the whirling motion of steam turbine, we are converting that potential energy of steam into the kinetic energy, and the turbine wheel is moving with certain angular velocity, that is angular motion, and that angular motion rotates a generator, and the generator is producing electricity. So this is actually the cause of learning this pure substance or phase change process. So for the particular reason, especially in thermodynamics, we are using pure substance. Like I'm talking about the water, we are in many thermodynamics or thermal power generation, we are using steam as a working substance to produce power. It is exchanging energy from heat to power. Like I've given one example. In the similar way, we can burn the coal power generation. Recently you have heard that in Thar we have discovered a lot of coals, and Anglo Power Gen company is extracting that coals, and not only extracting, it is creating power. They are producing power generation by heating this coal, and by these heating they are producing lot of steam, and that steam going to run the turbine, and then turbine is producing electricity. I was also in the English Biscuit Private Limited and in General Tire, so I was in power generation sector. I have very good knowledge how they are producing, and have an 5-year experience in boiler, how they are producing steam. And when I'm studying, when I taught this subject to electrical or urban infrastructure, urban department, I organize also a practical lab of the student. I arrange one class in my mechanical engineering lab, ensuring the actual equipment which producing the power. So their idea is they are getting more clear to the why we are studying this, how they are utilizing in the practical world what we are studying over here. So now moves on. Try to consider it. Don't get nervous or bored in this particular point, because in future we will solve very practical numerical, inshallah. So phase change process, we are studying phase change process. Consider a piston cylinder device containing liquid water at 20 degrees centigrade and 1 atmospheric pressure. It is state 1. For an example, like in this in the diagram you have seen that it is containing water at 20 degrees centigrade and atmospheric pressure. The H2O, water, is in the liquid form. It is called compressed liquid. In thermodynamics, the terminology used is compressed liquid or subcooled liquid for the liquid. It is not about to vaporize. It will not becomes steam definitely at 20. It will not. Heat is now transferred to the water until its temperature rises to say 40 degrees centigrade. It's a specific volume increase but remains as compressed liquid. And again the terminology used specific volume. So what is a specific volume? Is simply the volume divided by mass. Okay, so let's move on. as more heat transfer to the temperature, it keep rising until it reaches 100 degrees centigrade, but that is boiling state. At this point, water is still a liquid, but at any heat addition will cause some of the liquid to vaporize. Definitely, when we boil the water till the 100 degrees centigrade, it boils, and after that the temperature will not increase. If you you can do this experiment by yourself. You place the water into the stove and heat it, burn it till 100 degrees centigrade. The flame temperature is more than 100 degrees centigrade, but the water is not getting more, the temperature of water is not exceeding above 100. Why? Because the additional energy goes in creation of steam. So it is basically phase change process. So by studying this temperature versus volume gram, when we are heating the water till its boiling point, the volume is increased. If you see in this picture, by keeping the pressure, we need to increase the volume. By heating from 20 to 100 degrees centigrade, the volume of this system is increased because the pressure is constant. So in this graph temperature versus volume. As the temperature increase, volume is also increasing. We hold it we stick to this topic here, and in the lecture number 8 we will move further, inshallah.